I'm Professor Michio Kaku, and today we're venturing deep into a hidden layer of our own galaxy, one that astronomers never anticipated. For more than a century, humanity has scanned the stars using optical telescopes, infrared detectors, and orbiting observatories. We believed we had mapped most of what the Milky Way had to offer, but the universe, as always, had one more surprise. Recently, a new generation of radio telescopes, led by the MeerKAT array in South Africa, revealed something extraordinary: a population of faint, compact, ring-shaped radio structures scattered throughout the Milky Way. These are not distant galaxies. They are not background noise. They are real structures inside our own galactic neighborhood, structures that have been hiding in plain sight, concealed behind interstellar dust, undetectable by anything except powerful radio vision. And tonight, I want to take you on a journey, one that begins with a discovery and may end with a transformation in how we understand stellar evolution, feedback processes, and perhaps even previously unknown astrophysical mechanisms. This is the story of the Milky Way's unseen radio rings. Let's begin with the moment astronomers realized they had stumbled onto something groundbreaking. MeerKAT, a network of 64 radio antennas spread across the South African Karoo, was conducting a detailed survey of the galactic plane. It operates at 1.3 gigahertz, a frequency that cuts through dust clouds like an X-ray through skin. Where optical and infrared surveys hit a wall of interstellar dust, radio waves travel freely, illuminating the hidden architecture of the galaxy. During this survey, MeerKAT picked up 164 compact ring-shaped radio sources. Imagine that for a moment. 164 previously unseen circular structures, each less than an arc minute across, each faint, consistent, symmetrical, and inexplicably prevalent across multiple regions of the Milky Way. Many of these rings were invisible in infrared, others lacked optical signatures entirely, and some existed only in radio frequencies, hinting at processes that leave no detectable trace in any other wavelength. Right away, astronomers knew this was not a trivial anomaly. This was not noise, not interference, not a glitch. These rings had structure, coherence, and diversity. They varied in size, brightness, and internal complexity. Nearly 40% contained an infrared point source at their center. About 50% showed extended mid or far infrared emission. Nearly 20% displayed a central radio point source, possibly a dying star, a stellar remnant, or something even more exotic. And yet, a significant fraction had no identifiable counterpart at any other wavelength. Nothing in visible light, nothing in infrared, nothing in X-ray catalogs. They were effectively ghosts, radio-only structures with no obvious explanation. To put this in context, think of the so-called odd radio circles discovered around distant galaxies not too long ago. Those enormous, mysterious loops baffled astronomers when they were first detected. And yet here we are seeing similar ring-like shapes, but much smaller, right inside our own galaxy. It suggests that ring morphologies might emerge from multiple astrophysical mechanisms, not just one. It suggests that the universe recycles certain geometric signatures in ways we're only beginning to understand. But how did these rings evade detection for so long? The answer lies in dust. Vast clouds of interstellar dust that swallow visible and infrared light but allow radio waves to pass through. Our galaxy is essentially wrapped in veils. For centuries we've been looking through those veils and assuming we were seeing the full picture. We weren't. MeerKAT's unprecedented sensitivity and resolution cut through those veils. It exposed a layer of structures that had been invisible to generations of astronomers. For the first time, we could see the footprints of stars, dying stars, exploding stars, evolving stars, etched into the radio landscape of the Milky Way. Now let's dive deeper into what we think these rings might represent, because every one of them carries a story, a physical origin, and a consequence for the galaxy around it. One of the leading explanations involves planetary nebulae. When stars like our Sun die, they shed their outer layers, sending shells of gas and dust into space. These shells expand over thousands of years, forming circular or elliptical bubbles. Usually planetary nebulae glow in the optical or infrared, but if the central star has cooled, or if the dust shell is especially faint, radio emissions may be the only sign left behind. Several of the MeerKAT rings fit this profile: a quiet central source, smooth symmetry, and an infrared point that hints at a fading white dwarf. Another possibility is nova or supernova remnants. These explosive events send shock fronts outward in all directions, creating spherical shells of energized gas. Over time, the visible and infrared glow fades. What remains are faint, expanding radio rings, slowly dissipating echoes of a cosmic explosion. A number of the newly detected rings exhibit characteristics consistent with such remnants: uneven edges, faint central compact sources, and radio brightness profiles matching known shock structures. But not all rings fit into familiar categories. Some may be created by the intense stellar winds of massive stars, Wolf-Rayet stars, luminous blue variables, stars that sculpt circular shells through sheer force. Their winds create bubbles and cavities in the interstellar medium, often leaving behind radio signatures intertwined with infrared arcs. Still, some rings defy categorization. These are the ones that intrigue me the most, the ones with no infrared counterpart, no optical presence, nothing but radio. Could they be gravitational lensing artifacts? Could they be galactic analogs of odd radio circles created by shock fronts, jets, or turbulent magnetized gas? Could they be the footprints of transient events we've never directly observed? These unanswered questions remind us that our galaxy still hides secrets in its deepest layers. But beyond the scientific intrigue, these rings matter for a larger reason. They fill a major observational gap. They represent a population of stellar remnants and shells that were too faint, too obscured, or too small to detect before. Their existence implies that late-stage stellar activity, mass loss, eruptions, feedback processes, may be far more common than our models predicted. Each ring is a time capsule, a frozen moment from a star's life cycle. Some tell the story of a star's final breaths. Others tell the story of shock waves rippling through interstellar gas. And collectively, they reveal something profound. Our galaxy is far more dynamic, more turbulent, and more layered than we ever imagined. This brings us back to the theme of discovery. When we push technology forward, when we build telescopes sensitive enough to detect faint whispers in the cosmic noise, the universe rewards us with surprises. MeerKAT was designed for precision, depth, and clarity. It delivered all three, and in doing so, it has changed the way we look at the Milky Way. In the next section, we will explore the deeper scientific theories behind these rings, the physics that could generate such shapes, and why this discovery may fundamentally reshape our understanding of galactic evolution. Stay with me. As we continue our journey into these mysterious radio rings hidden inside our galaxy, it becomes clear that understanding their origins requires more than cataloging their shapes. We must peel back the layers of physical processes that generate such structures. Rings in nature rarely form by accident. They are signatures, footprints, left behind by powerful mechanisms shaping the Milky Way from the inside out. I'm Professor Michio Kaku, and now we explore the physics behind these enigmatic patterns. Let's begin with the explanation that aligns most naturally with what we know, the final stages of a sun-like star's life. When a typical star exhausts the nuclear fuel in its core, it undergoes a quiet but dramatic metamorphosis. It swells into a red giant, sheds its outer layers, and forms an expanding bubble of gas and dust. These shells are what we call planetary nebulae. Over tens of thousands of years, they drift into faintness, but their structure remains a hollow, glowing sphere with a dim central star, sometimes only detectable in radio. Several of the newly discovered rings carry exactly these traits. The symmetry is smooth. The radio emission is faint but uniform. Some contain a subtle infrared signature in the center that likely corresponds to a white dwarf cooling in solitude. These rings are cosmic tombstones, the last visible traces of stars long past their prime. But planetary nebulae alone cannot explain everything MeerKAT detected. Many rings show sharp edges, irregular intensity gradients, or faint internal knots, all hallmarks of explosive events. Consider a nova or even a supernova. When the thermonuclear surface of a white dwarf ignites, or when a massive star collapses, the resulting shock front blasts outward in all directions. Initially, these explosions flood the sky with energy in every wavelength: X-rays, gamma rays, optical light. But as centuries pass, that brilliance fades. What remains is a faint, circular shock boundary expanding into the interstellar medium. Some of the MeerKAT rings fit this category so well that astronomers suspect they are ancient remnants of once luminous events. Their radio signatures carry the fingerprints of accelerated electrons spiraling along magnetic fields, a thermal and non-thermal mixture consistent with known supernova shells. These are fossil explosions still echoing through the galaxy. Yet another possibility arises when we consider the most massive temperamental stars known to astronomy: Wolf-Rayet stars and luminous blue variables. These stars do not need to explode to leave behind rings. Their stellar winds are so powerful that they turn space itself into sculpture. Imagine a wind 1,000 times stronger than our sun's, pushing against the interstellar medium with incredible force, carving out bubbles, creating arcs, and shaping shells. These structures tend to emit in both infrared and radio, and indeed, many of the detected rings show extended mid or far infrared emission alongside their radio profile. In these cases, the ring is not the aftermath of death. It is the signature of violent life, a monument to a star burning so intensely that it reshapes the cosmos around it. However, not all of the detected rings can be neatly placed into known categories, and these outliers may hold the biggest clues to new physics. Some rings show no infrared source, no optical counterpart, and no central object at all, nothing except a clean, coherent radio circle. How do we explain a ring that exists only in radio? One tantalizing possibility is that some of these structures could be galactic analogs of odd radio circles, those mysterious large rings discovered around distant galaxies. Theories for ORCs include shock waves from massive energetic events, relics of past activity from supermassive black holes, or even ancient interactions between magnetic fields and turbulent gas. If scaled-down versions of such phenomena exist inside our Milky Way, they would represent a new class of astrophysical structures, hinting that ring formation may be a far more universal pattern than previously believed. Another intriguing hypothesis is gravitational lensing, mass-bending light from objects behind it, forming ring-like appearances known as Einstein rings. While most of the MeerKAT detections do not match typical lensing profiles, it remains a possibility for a small subset. But the majority of these rings likely have physical structure, not illusion. They are not distortions. They are real shells of real material expanding in real space. Still, the most exciting aspect is not one specific explanation, but the diversity itself. The rings do not point to one type of star, one type of explosion, or one type of event. They point to a galaxy filled with continuous transformation, where dying stars, erupting stars, massive stellar winds, and ancient shock fronts all leave behind loops, arcs, and shells that overlap to form a hidden radio architecture. MeerKAT has allowed us to see this architecture for the first time. But why does this matter? Why should we care about faint structures a few light years wide, buried behind dust clouds? The answer lies in feedback, the way stars shape the galaxy around them. Every ring tells us something about energy being injected into the interstellar medium. When a dying star releases gas, it enriches surrounding space with heavy elements. When a shock front expands, it stirs turbulence, compresses gas, and sometimes triggers new star formation. When stellar winds carve bubbles, they redistribute matter and influence magnetic fields. The Milky Way is not static. It breathes, churns, recycles. These rings are part of that process. For decades, astronomers believed that only the brightest remnants, the obvious supernova shells, the glowing planetary nebulae, played a significant role in galactic recycling. But the discovery of more than 160 faint rings in a single survey suggests something far greater. If one region of the sky contains this many hidden remnants, then the entire galaxy may be filled with thousands. Our count of stellar end-stage events, novae, supernovae, mass loss episodes, may be drastically underestimated. These rings force us to reconsider galactic evolution models. They shift the statistics. They redefine how often stars shape their environment. And the implications extend further. Because these rings occupy a regime between bright, well-known nebulae and structures too faint to detect, they fill an observational void. They represent a missing link in our understanding of how energy flows through the Milky Way. Like fossils filling in evolutionary gaps, these rings fill in astrophysical gaps. They are evidence that quiet events, low-energy eruptions, weak shocks, slow mass loss, may collectively play a larger role than we thought. Most importantly, these rings highlight the revolution underway in radio astronomy. For decades, radio telescopes were limited in sensitivity, but MeerKAT's advanced design, its broad bandwidth, low noise, and exceptional imaging capabilities makes it possible to detect faint objects previously lost in the noise. And this is only the beginning. When the square-kilometer array becomes operational, we will be able to map the galaxy at a level of detail we once considered science fiction. We will see every shell, every bubble, every ripple left behind by the life and death of stars. In the next chapter, we'll examine what comes next, the surveys, the follow-up observations, and the future of radio astronomy as we prepare to uncover an even deeper layer of the Milky Way's hidden structures. As we arrive at the final chapter of this journey through the Milky Way's hidden radio rings, we shift our attention toward what lies ahead. Discovery is never the end of a story in science. It is the beginning of a new era of questions, tests, and deeper exploration. I'm Professor Michio Kaku, and now we look toward the future of these strange and beautiful structures scattered throughout our galaxy. The discovery of more than 160 faint radio rings in a single MeerKAT survey tells us something profound. The Milky Way is not simply a disk of stars orbiting a central black hole. It is a living, breathing ecosystem shaped constantly by energy, shock fronts, mass loss, turbulence, and the aftershocks of stellar evolution. These rings, small, faint, and previously invisible, are the scars and signatures of that cosmic activity. They expand our understanding of how matter moves, how elements scatter, and how the galaxy renews itself. But we are only at the beginning. To unlock the full meaning of these rings, astronomers must now embark on a series of deeper, more targeted investigations. Multi-wavelength follow-ups will be essential. Infrared surveys can identify hidden central sources. Optical observations may detect faint remnants or scattered light. X-ray telescopes can reveal hot gas or high-energy particles associated with explosive origins. Each wavelength offers a piece of the puzzle, a different window into the physics shaping these shells. Spectral studies will help determine whether the emission is thermal or non-thermal, whether the rings come from warm ionized gas or from electrons spiraling in magnetic fields. Polarization measurements can map the magnetic structure of these shells and reveal how turbulence or compression shape them. Time series observations will track whether any of these rings are expanding, evolving, or changing brightness over months or years. Even subtle variations can reveal their age, origin, and energy source. But perhaps the most transformative step is still to come. When the Square Kilometer Array, SKA, begins operations, it will become the most sensitive radio instrument ever built. With its unprecedented resolution and collecting area, SKA will be able to survey the galaxy with a clarity that makes MeerKAT look like a first draft. If MeerKAT found 164 rings in one region of the sky, SKA may find thousands. It may map the full hidden architecture of the Milky Way, revealing every faint shell, every quiet relic of past stellar activity. It could even uncover entirely new categories of radio structures, expanding our taxonomy of cosmic phenomena. Imagine a full galactic atlas of rings, arcs, bubbles, and shells, a radiographic image of the Milky Way's skeleton, each structure a marker of energy release, each ring a memory of a star's transformation, each bubble a chapter in the galaxy's ongoing evolution. As this catalog grows, astronomers may develop new classification systems. We may distinguish between classical planetary nebulae, stellar wind bubbles, nova remnants, supernova echoes, and more exotic structures born from turbulent magnetic interactions or large-scale shock fronts. Some categories may align neatly with known physics. Others may challenge existing models and force us to rethink how stars live, die, and influence their surroundings. And that is the true power of this discovery. These rings are not simply pretty patterns in radio images. They are evidence, physical, measurable evidence, that the Milky Way is far more active, more restless, and more complex than earlier generations believed. They shift our statistical understanding of stellar life cycles. They redefine the frequency of eruptions, mass loss events, and shock processes. They reshape our models of how gas compresses, how turbulence spreads, and how new stars are born from the ashes of older ones. For decades, astronomers focused on the brightest objects, glowing nebulae, massive supernova remnants, and dramatic stellar explosions. But now we see that the galaxy's quiet events, its faint echoes and subtle shells, may be just as important. They are the small pulses in a vast cosmic heartbeat. As we close this exploration, remember that every discovery, no matter how faint or hidden, adds to our understanding of who we are in the universe. These rings, once invisible behind clouds of dust, now illuminate the Milky Way with new meaning. They remind us that the cosmos is layered, mysterious, and filled with phenomena we have yet to understand. And with the next generation of telescopes, we stand on the edge of a new chapter, one where the galaxy reveals its deepest, most delicate structures. I'm Professor Michio Kaku. Thank you for joining me on this journey through the unseen architecture of our galaxy. Stay curious, keep exploring, and remember, every time we open a new window on the universe, we find something extraordinary waiting on the other side.